As they took the stage on April 26th of 1920 at the Smithsonian Museum of Natural History, the two astronomers sought to address one of the great scientific questions of their day. Just how big was the universe? How vast the cosmos? On one side was the young, dynamic, and by some accounts reckless staff observer from the Show Me State who had once reported on crime syndicates in Joplin, Missouri. On the other was an astronomer's astronomer, and president of the prestigious Astronomical Society of the Pacific, who had inherited a legacy at what had once been California's greatest observatory, only recently eclipsed by the institution his opponent now worked for. The debate the two were to participate in had been several years in the making, but now they were called upon to present the argument for the sides they had come to be the spokesman for, at least in the United States. Harlow Shapley came to say that there was only one galaxy of stars, and that the spiral nebula, now so commonly observed in places like Harvard, Lick, and Mount Wilson, were accumulations of gas and dust within that vast conglomeration. Heber Curtis, his opponent in the debate, would present the evidence for the idea that these spiral nebulae were, in fact, island universes in the language of the philosopher Immanuel Kant. Immense collections of stars like our own galaxy that were much further away than anyone had imagined even at the turn of the century. The audience had come to hear a lively give and take of scientific ideas and evidence, and they were not disappointed as the two astronomers laid out the cases for their respective positions. While some observers would later say that Curtis was the better presenter and that Shapley's delivery seemed fairly flat, the consensus was that neither man had sufficiently made a solid case to resolve the issue. In fact, many would side with Shapley as they found the idea of a cosmos as vast as Curtis was suggesting it to be more than they could imagine. After the event was concluded, the debate continued in the pages of the Bulletin of the National Research Council, where each man offered specific counter-arguments to the evidence offered by the other man in the form of review papers published therein. It was a model of how scientific debate and communication was to be done, though, by the Bulletin's publication, both men had moved to new positions. Shapley to take up the directorship of the Harvard College Observatory, and Curtis a similar position with the Allegheny Observatory at the University of Pittsburgh. The great debate, as it came to be known, was inconclusive in that it didn't arrive at a conclusion, but that was really never the point. Truth be told, there wasn't enough evidence to settle the question. Instead, the point of the event was to make known to all astronomers in the United States the state of the question and the research being done to address it. What neither man knew was that, as they were writing the papers, the tools and the person who would so powerfully use them had been brought together at Mount Wilson. In 1922, it would be another Missourian, by way of Chicago, Oxford, Kentucky, and Indiana, who would use the world's most powerful telescope and Miss Leavitt's law to resolve the question and make for a cosmos bigger than anyone could have imagined. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 40, The Great Debate. Once again, to move forward in our narrative of humanity determining its place in the cosmos, we have to navigate backwards up another tributary stream. This stream will share a number of similarities with others that we have explored with the now ubiquitous telescopes and photographic plates. But as in the other watersheds we have investigated, the focus of the research will be different. Rather than stellar spectra and photometric comparisons, the emphasis will be on resurrected technologies and emerging smudges that will resolve into great pinwheels of light. As we move through the story, we will find another feature familiar to us, the largesse of wealth in sponsoring both the work being done and the creation of the tools so important in making progress to finding the answers to the questions being asked. As we saw at Harvard with the philanthropy of Anna Draper and Elizabeth Bruce, the discoveries we'll discuss in this episode were made possible by industrial magnates with names such as James Lick, a man by the name of Yerkes, and Andrew Carnegie. In this, we will also see a shift from the institutions on the East Coast associated with the Ivy League to the mountains of the far West, first on Mars Hill in Flagstaff, Arizona, and then in California, from those areas perched over San Francisco down to the area of Pasadena. So where do we start? I think the best location is in the same place that Marcia Bartusak does in her book that serves as the source for this episode, The Day We Found the Universe. And it's in the Diablo mountain range that overlooks the San Francisco Bay. On what was once known by the Spanish explorers as La Sierra de Isabel, and later dubbed Mount Hamilton by Charles Hoffman for his friend and Presbyterian minister Laurentine Hamilton, the entrepreneur James Lick funded what was the first permanently established high-elevation observatory, at least high elevation of the time, in 1888. Designed and built in the classical style of the period, the main observatory building looks nothing so much as a European palace with hand-carved moldings and curved wooden planks. It housed the largest refracting telescope of the time, but interestingly, at least for our story, that's not really where the groundbreaking work was going to be done. Down a quarter-mile trail along what is known as Ptolemy Ridge was a more modest structure that reminds one of a small chapel. Within its dome, however, was the facility's problem child. Known as the Crossley Telescope, it was a 36-inch reflector that had been built in England by the Londoner Andrew Common and had been used to take one of the first images of the Orion Nebula. Sold to Edward Crossley, a wealthy textile manufacturer, it was first moved to Yorkshire, where the location was deemed unsuitable for the doing of good astronomy. It was then donated to the University of California and installed at the Lick Observatory. Unfortunately, since its original designer did not make the trip, and the staff at Lick felt reflectors to be inferior to refractors, only half-hearted efforts were ever made to get the instrument operating correctly, and it quickly fell into disuse. However, what the installation of the telescope did do was precipitate a crisis between the observatory's director and its observing staff that resulted in the former's dismissal. He was replaced by a guy that was then the director of the Allegheny Observatory at the University of Pittsburgh, one James Keeler, who had begun his professional career as a staff astronomer at the Lick Observatory before moving to Pittsburgh. Now, I wish I had more time to go into Keeler's biography here, but unfortunately, we have a good bit of ground to cover, so instead I hope to include him in a biographic episode. What we can say was that Keeler was something of what I would call a bleeding edge guy when it came to technology and its incorporation into astronomy. In many ways, he mirrors Edward Pickering in both his desire to push new technologies and his understanding that spectroscopy was the future of astronomical research, and thus he became the United States' foremost expert on the technique, using it and the newly established Doppler effect to confirm James Clerk Maxwell's theoretical work on the nature of Saturn's ring as consisting of many thousands of individual particles, all orbiting the massive planet due to gravitational forces. Thus establishing his bona fides, he was tapped to lead the Lick Observatory in 1898. Now, Keeler's other research interest had been the spiral nebulae that had first been observed by William Herschel and later by the Earl of Rosse with his gargantuan Leviathan in Scotland. Now, Keeler's other research interest had been the spiral nebulae that had first been observed by William Herschel and then later by the Earl of Rosse with his gargantuan Leviathan situated there in Scotland. He had worked on photographing them and trying to capture their spectra while in Pittsburgh, but had been stymied in making much progress by the sooty skies and comparatively poor instrumentation at the Allegheny Observatory. Upon his arrival as the new director there at Lick, Keeler surprised his staff by not making claim to the facility's main telescope, but instead declared that he would leave the research projects presently using it undisturbed while he would focus on getting that disreputable Crossley reflector up and running. He had an understanding that mirrors would be eventually much more effective when doing spectroscopy, as they didn't tend to absorb specific wavelengths of light the way glass lenses did. And so he was happy to try to get the old beast running if it offered him a chance to work uninterrupted and get better data. While there were a plethora of issues to be resolved, Keeler persevered, in part because he was both the director and the research astronomer who desired to use the instrument, and in time, each of those obstacles was overcome, and 4 months after his arrival on Mount Hamilton, Keeler took his first good photographs using the telescope. His first paper from those photographs was on the comet Brooke that appeared in the California skies in the fall of 1898. His photographs of the object were the first to capture a comet in such detail, and interestingly, in that particular case, it revealed that the comet had a double nucleus. This work, coupled with additional work done on the imaging the Pleiades star cluster and the Orion Nebula, convinced him, and not just a few others, that reflecting telescopes were likely the future of astronomy. To understand the jolt these photographs created in the astronomical community, one needs only think of the images returned from the Hubble Space Telescope shortly after its mirror flaws were corrected. And as an aside, there actually are a remarkable number of similarities between the story of the Crossley and the Hubble Space Telescope that we really can't go into now. The important thing to understand is that the clarity and detail of the images that Keeler collected transformed what was thought to be possible in terms of astronomical scientific research. It wasn't until April of 1899 that Keeler started looking at the spiral nebula he first had come to Mount Hamilton for. The first one he looked at was M81 in the constellation of Ursa Major, the collection of stars that contains the familiar Big Dipper, or Plough sometimes is what it's called. Previously, the nebula had just shown as a circular sort of fuzzy patch of light, but in Keller's image, there was a very clear indication of what is known as spiral structure. Unfortunately, due to misalignment of the telescope, the stars in the picture were streaked, thus rendering the image useless from a research perspective. In May, however, Keeler turned the reflector to Rosse's Whirlpool Nebula, also known as M51, and took a 4-hour exposure of that object. The photograph was truly remarkable, capturing detail and structure never before imagined. Just as importantly, though, the image of that small region of the sky, about the size of 2 full moons, showed 7 more spiral nebula that had been too faint to be seen by any other instruments. Now, Keeler initially thought that this finding was something of an aberration, kind of an unusual random grouping of unrelated objects. But as he began to take more photographs, he soon realized that far from being the exception, it was very much the norm. As he began estimating numbers from these photographs taken from all around the sky, he came up with what he admitted was probably a very conservative figure: 120,000 spiral nebula within the seeming limits of the Crossley, spread out all across the skies, visible from Mount Hamilton in California. Moreover, with such a large sample size to draw from, he saw different spiral nebula from a whole variety of angles, from face-on to seeing the disk edge-on, thus allowing him to build sort of a comprehensive picture of what was beginning to be seen as a common astronomical structure. Some of these spiral nebulae were larger and brighter, while others were smaller and dimmer, and thus began to give rise to the question of their composition and distance from the observer. In other words, were they smaller conglomerations of gas and dust, or maybe stars or both, that were a lot closer to us, or were they enormous collections of matter at some immense distance heretofore unmeasured? In 1900, there was no way to determine the distance, as resolving individual components in these nebulae, as they were known, was just about impossible. Some thought, and Keeler was among these, that these were gas and dust that were spiraling in to form a new star, and if Immanuel Kant and Simon Laplace had been correct in this nebular hypothesis of the formation of our solar system, the attendant planets that would go with that process. The other idea is that this nebula might be enormously far away, as island universes is what they were called, each like the Milky Way, containing an untold number of stars. In both cases, the spiral structure, often with clearly visible arms spiraling out from the center, indicated a sense of rotational motion. One of the more poignant questions here to contemplate at this point is whether Keeler himself might have been able to answer any of those questions had he not died of a complication of smoking just a short time later. Given his expertise with spectroscopy and his superior telescope and observing position, there are those who feel very confident that he would have accumulated the needed evidence to settle that question. Moreover, with said data, he might well have arrived at the conclusion of an expanding universe some 3 decades before what that had actually ever been discovered. However, his habits and fate conspired to bring an end to his life on August 12th of 1900, just a month shy of his 43rd birthday, after a series of strokes brought on by either double pleurisy or emphysema or lung cancer. Whatever the case, the death was tragic, and Harvard's Pickering would write of Keeler's death that the, quote, loss cannot be overestimated. There is no one who seemed to me to have a more brilliant future, or on whom we could better depend on for important advances in work of the highest good, end quote. Thus, having brought both the reflecting telescope and the spiral nebula to the center of the astronomical stage, James Keeler took his bow and departed the production. This is probably a good place to take a moment for a digression into the nature of scientific discovery and the role that emerging technology plays in that process. In my Science, Pseudoscience, and Snake Oil colloquium, I have my students do an exercise, and I think I've described it in this podcast before, but it's an exercise in hypothesis formation and modification, where I give them pieces to a puzzle in a series of stages, sort of like doling out data a little bit at a time. After each small set of pieces is given out, each group of students has to form a hypothesis of what the puzzle is going to be a picture of. After a few wild guesses based on the really limited data that they start with, most of the groups begin to hone in on what is a more correct idea of what that picture actually is. But what they don't know, and what I don't tell them, is that I've kept about a dozen or so of the 100 pieces back, in a bag where they can't see them. These pieces represent a very important part of the image in terms of understanding the picture in its completeness. Thus, as they go about their work, first of coming up with descriptions of the picture and then of putting the puzzle itself together, they aren't going to get the full thing until, at the very end of the exercise, I show them the box that the puzzle came in, and they realize what they've been missing. So why do I do this? What's the point of the exercise? Why do I hold back those pieces? When we do science, our ability to observe the physical universe is limited either by our senses or by the tools we use to extend those senses. Hence, there may be pieces of the picture that are actually unavailable to us. Because of this, there will be a hole in our understanding that we either have to fill through inference or informed speculation, though, as we've occasionally discussed, it's easy for that speculation to become untethered from reality if we let our exuberance get the better of us. This is where Keeler's use of the Crossley reflector is really, really important. As will be realized with the building of the 1-meter refractor at the University of Chicago's Yerkes Observatory, there are limits to how big you can make a lens from glass before it begins to bend under its own weight and distorts the image of anything you're trying to observe. Thus, if refractors are the only kind of quote-unquote good telescopes that you can build, your technology gets stuck, and in 1900, that's pretty much exactly what happens. However, with that unique way of silvering a mirror, which was, by the way, a new process at the time, and a design that placed the main obstacle element at the bottom of the telescope where the structure of the tubes can be reinforced, thus significantly reducing the warping of the optical element, the reflecting telescope design once again becomes a viable option for making good astronomical measurements. Motorized drives, as they matured, would allow for even more precise guiding and with that, longer exposure times when taking photographs. Because of these advances, after 1900, no observatory will build a research telescope that isn't a reflector, and a lot of that has to do with Keeler's success with the Crossley telescope. This will be the technological jump that, when fully realized, will allow astronomers, first at the Mount Wilson Observatory, and then at places like Mount Palomar, Kitt Peak, and nowadays Mauna Kea, Hawaii, the Atacama Desert in Chile, and La Palma in the Canary Islands, to make huge strides in observing. Without Keeler's willingness to take a risk on a new technology, or actually in this case an old technology significantly upgraded, all of the work henceforth would have been impossible. Remember from our past discussions on optics, not only do bigger mirrors allow the astronomer to observe fainter objects, they allow him or her to better resolve between two more closely spaced objects, something we call resolution. This was why Shapley was able to distinguish Cepheid and RR Lyra variables and globular clusters using the 60-inch reflector at the Mount Wilson Observatory, and while the 100-inch Hooker telescope on Mount Wilson would be constructed, that's going to be so important to our story down the road a little ways. So, to return to that story, things will remain in the state that Keeler left them more or less for the next 15 years or so. And when I say that, what that means is you're going to have one individual who's going to be running the Crossley, taking data mostly associated with spiral nebulae. The question would remain hanging for others to nibble at, that, what's the scale of the universe? But there was a lot of other stuff going on, much of which we've documented in our other episodes. There's the work at Harvard in classifying stellar spectra, cataloging variable stars, and developing methods of doing accurate photometry from photographic plates. During this time, there's also other places doing excellent work in each of these other areas, including places like the Lowell Observatory in Flagstaff, Pittsburgh's Allegheny Observatory, the University of Chicago and its Yerkes Observatory, and a new facility in the mountains overlooking sleepy Pasadena, California. Now, to continue at Lick, though, the work on spiral nebula would continue, though for a time at a pretty reduced pace. One result of note was based on an observation made by Julius Scheiner of the Potsdam Observatory, who was able to take a somewhat detailed spectrum of the Andromeda Nebula in early 1900, about the same time that Keeler was doing his last work. And while it was a crude spectrum, compared to the spectra being taken of stars or nebula like the Orion Nebula, it showed a surprising result. The spectrum was much more consistent with what one might see if observing a large collection of stars than if one observed a luminous clump of gas and dust. While Scheiner's result was initially more or less ignored by everyone but Keeler, it was taken up by a young graduate student by the name of Edward Fath, who used the Crossley telescope to confirm the findings for Andromeda and another number of other spirals. Given the instrument's superior ability to track the sky and its stable mount, he was able to get exposure times in excess of 18 hours on a single plate and show, without a doubt, the accuracy of Shiner's result. The spectra of spiral nebula were made by large numbers of stars, and of that there could be no question. Unfortunately, this idea really contradicted what was at that point in time the dominant solar nebula hypothesis that held that these spirals were made of condensing gases, and so Fath didn't really push the idea, in part on the recommendation of Keeler's replacement as the director at Lick, W. W. Campbell. Given this, Fath's publication, with a fairly weak conclusion, was basically ignored or overlooked by most of the astronomical community. And when he finished his PhD work, he moved on, and in his place at the Crossley, a new person stepped in, a person by the name of Heber Curtis. Now, Curtis had been hired in 1902 as a staff astronomer and had been sent to Chile in 1906, just before the San Francisco earthquake, to run Lick's Southern Observing Program there. He had been recalled back to Mount Hamilton in 1909, just as Fath was finishing up. Now, what should be noticed here is that unlike Fath, Curtis was an established astronomer who had no difficulty pushing whatever ideas his data led him to. During the years after 1910, the island universe idea, once in serious eclipse as we mentioned, began to make a comeback. This was in part due to the promotion of it by the well-known British astrophysicist Arthur Eddington, who found the hypothesis just grand and captivating. A great popularizer of astronomy and astrophysics through his writings, Eddington held up a view that this grand idea of a huge universe filled with many great conglomerations of stars spread across the incomprehensibly vast reaches of space was a more satisfying and beautiful hypothesis than the solar nebula one was. In promoting the idea, Eddington brought forth the evidence to support it that had languished. Now, one of those who believed in Eddington's vision was Curtis. Along with him, Campbell was convinced that this really was an open question, worthy of continued research and allocation of resources, and so Curtis was allowed to continue Keeler's work with the Crossley. A fairly gifted mechanic and tinkerer, Curtis made a number of improvements to the observing platform and the driving motor for the telescope mount. By the way, for my Bay Area listeners, shout out to you guys again, the Crossley is still in use actually right now as an extrasolar planet hunter, more or less in the same condition Curtis left it in when he left the observatory. And so it's there with this improved metal tube that makes it look a lot like something you might see on a battleship. And you can take tours of the Lick Observatory, and if you hike down the trail, I know the crew would just love to see a few pictures of the instrument, if you know what I mean. Hint, hint, wink, wink, nudge, nudge, nod, nod, you know. Anyway, in 1910, he used the Crossley to observe the return of Halley's Comet, taking over 400 pictures of it. He then turned it to the hunting and observing of spirals and quickly doubled the number contained in Lick's photographic plate collection. One of his goals there was to attempt to observe rotation of the galaxies, or nebula actually as they were known then, from the plates taken far apart in time. As Keeler's plates were taken in 1900, Curtis thought that if the spirals were made of condensing gas, one might be able to detect rotation in at least a few that had occurred over the course of that intervening decade. When he was unable to observe any rotation when comparing images taken by Keeler and then updated by him, he began to think that he had pretty compelling evidence that these spirals actually were other galaxies. The other argument that he began to believe in very strongly was that while he was able to photograph spirals in many locations with respect to the Milky Way, there was what was called a quote-unquote zone of avoidance, where no spiral nebulae could be found. The reason for this, he argued, was that if the spirals were indeed outside of our own galaxy, the plane of our galaxy, talked about our galaxy being this big flat disk, if you're looking through that disk, the light from all of the stars of that disk would block our view of those outwardly existing spirals. Conversely, though, if those spirals were inside the Milky Way, we should still be able to see a somewhat reduced number of them even in those zone of avoidance directions. given that we see next to no spirals in that region, was evidence, in Curtis's mind, that the spirals had to lay outside the Milky Way. In the years from 1910 onward till about 1917, 1918, Curtis would become a principal proponent of the island universe hypothesis in the United States, giving lectures and writing papers in support of it until it was once again seen as a truly viable alternative to the solar nebula hypothesis that Keeler's and so many others had supported just a decade earlier. In other words, by the time Curtis gets done, there really is a lot of scientific discussion about which way this is going to go. In 1917, just as the U.S. was considering entering into the Great War, a number of nova were seen in various spirals, including 3 that had actually been observed by Curtis. This set off a race to find candidate events in older plates, and there were several actually located. The problem, though, was that while some of these events were fairly faint, the most recent 1 or 2 were actually really, really faint. Now, if this were the case, that meant that the earlier novae argued for the spirals to actually be a lot closer than was generally thought of in the island universe hypothesis. Curtis, though, resolved this conflict by suggesting that there were actually 2 types of novae, regular novae and supernovae. Regular novae were the types that had up until now only been seen in the Milky Way itself. We talked a lot about these when we were doing the Harvard College Observatory episodes, where they would find on the plates, especially that first one that they found by Solon Bailey down on the South America plates, where a star would get extra bright really quickly and then fade away. Now, when viewed from very far away, Curtis thought, these would be so faint that they would have been missed by any earlier studies and would only be visible to instruments like the new 60-inch reflector at Mount Wilson, where the most recent one had actually been seen. The other, brighter novae were of a different type, a kind of event that had never actually been witnessed directly in the Milky Way. The earlier brighter novae that had been seen in the Andromeda spiral, for example, he thought were actually this brighter supernova type. Now, to be honest, this is actually a pretty post hoc, we call it, or after the fact type of argument, and so it was really looked upon with a lot of skepticism by many, as we'll see. The idea of positing 2 types of nova violated what we call Occam's razor, which states that one should not introduce any unnecessary elements into an explanation. If one type of nova could still explain the observational data, why introduce a second to preserve a hypothesis that really wasn't thought to be all that strong? Unfortunately, Curtis wasn't able to follow up on the research to gather data in support of his hypothesis because war broke out and he got called on to do a whole bunch of other things. In 1918, in Washington as part of the National Bureau of Standards, Curtis was finishing up some work in relation to the recently signed armistice, and he was asked to give a talk about the Milky Way before a joint meeting of the Washington Academy of Science and the Washington Philosophical Society. In it, he was very direct in putting forth a smaller size for the Milky Way with the Sun in the center and the spirals representing island universes. In it, he laid out his evidence, including the idea of the 2 nova types, though this time he had a whole lot more evidence to support that idea. The whole talk was very well received and made Curtis just a bit of a celebrity, at least on the scientific speaking circuit. He was asked to stay in D.C., but instead returned to the Lick Observatory to continue his work. He was gone, but he was not forgotten, and in just a year, he would be back to defend his ideas. So now, let's turn our attention to a couple of the other places where other work was taking place. In Flagstaff, Arizona, Percival Lowell's competitive streak drove him to order a spectrograph that was an improvement to the one Keeler had been using at the Lick Observatory. To run it, he hired Vesto Melvin Slipher, recently graduated from the University of Indiana. VM, as he was known by his friends, had grown up under the dark and open Midwestern skies of America and had developed a penchant for both mathematics and machines. He had graduated with degrees in both celestial mechanics and astronomy, and so when he arrived on Mars Hill, as the Flagstaff Observatory was known, he was both supremely prepared and more than a bit intimidated by the challenges that faced him. Nevertheless, with his trademark patience and tenacity, and over the course of a year, he learned not only how to operate the complex new spectrograph, but also how to extend its utility. Originally designed to take planetary spectra, he was able to develop methods that allowed it to be used for deep space objects as well. Now, as a side note here, I've mentioned Percival Lowell in passing a couple of times over several episodes, and I should probably say just a bit more about him. The son of a well-connected and wealthy Boston family, Lowell would major in mathematics at Harvard and would become fascinated with astronomy in general and Mars in particular. This would lead him to build a first-rate, high-altitude observatory in Flagstaff in order to get the best viewing possible. That the University of California soon pursued the same goal set off a competitive streak in him that meant he would never allow his observatory to fall behind his rivals, most notably the Lick Observatory up there near San Francisco and Mount Wilson. While the comparison is inexact in some ways, there are more than a few similarities between Lowell and a certain chief executive that happens to, reside sometimes in a White House, in terms of being flamboyant, aggressive, desirous of celebrity and fame. One sort of has to wonder what Percival Lowell's Twitter feed would have been like had social media existed at the turn of the 20th century. While I probably won't do a biographical episode of Lowell during this series, I would like to return to his story as part of a possible discussion of the perils and pitfalls of scientific communication. If you're at all familiar with his whole fascination with canals on Mars, that's something to look forward to. So anyway, back to Slipher. Slipher was actually in a pretty good place because he worked well under Lowell, because he sort of had an opposite type of personality that was comfortable with his boss hogging the limelight, or, in this case, as electricity advanced across the continent under the work of men like George Westinghouse, the spotlight. Slipher was able to use the spectrometer first to determine the Doppler shifts of spectral lines taken from the atmospheres of Jupiter, Saturn, and Mars, thus allowing him to calculate their rotational rates. By 1909, he was able to confirm the presence of gas in the space between the stars, a result that would take others like Shapley far too long to accept. By 1912, he had modified his spectrometer to be able to take spectra more rapidly, and so it was determined to take the spectrum of a spiral nebula in a great bit more detail than had been done before, and to see if he could get a measurement of how fast that spiral nebula was moving towards or away from us. So he started out by selecting the Andromeda Nebula, as it was known, at the time. That's what we called it then. And then over the course of several months, he refined his observational procedure to be able to get a clear spectrum of the nebula for the first time ever. By January of 1913, he had finally had 4 really good spectra of the nebula, and so he was able to start measuring the Doppler shifts from those spectral plates and calculating to come up with what the nebula's velocity was. And what he found was really astonishing. The Andromeda Nebula, according to his observations and calculations, was moving towards the Earth at a rate of 300 kilometers a second, about 10 times the velocity of an average star. Stunned at the result, he sent copies of the plates and calculations to his colleague at Lick, the man we've already discussed, Edward Fath. Fath had told Slipher sometime earlier that he had attempted to measure the velocity of the nebula all the way back in 1908 and had gotten some anomalous results, or at least results he thought were anomalous. Chalking them up to his telescope error, Fath had sort of forgotten about the whole thing until he received Slipher's data with a note asking him to check the work. Going through Slipher's data and calculations, Fath realized that he had found the same thing a few years earlier and had absolutely missed their significance. Gotta tell you, Fath has had some pretty bad luck in this story, hasn't he? Now, this was really a huge result, and with a bit of prodding from Lowell, Slipher would extend his methods to attempt to measure the velocities of several other spiral nebulae, something that, by the way, took a lot of time to do. By the summer of 1914, He had velocities of 14 different spiral nebulae, and with the exception of the Andromeda Nebula and 2 others, they were all moving away from the Earth, some with velocities 3 or 4 times that of the Andromeda Nebula. And this was really big news for the island universe proponents. It was hard to imagine clouds of gas and dust moving between 10 and 50 times faster than the stars that were supposedly born out of them. Moreover, it was felt that at those speeds, it seemed that given the vast amount of time that they might have been moving for, they would have flown out of the Milky Way. Arguing against this point would be the measurements of Hertzsprung to the Magellanic Clouds and later Shapley's estimate of the size of the Milky Way based on the globular cluster data he had. Now, it should be noted here, though, that Hertzsprung believed that Slipher's results supported an island universe's hypothesis, an idea with which he agreed. What is fascinating is that when, in August of 1914, as the crisis in Europe deepened towards war, Slipher presented his results to the newly named American Astronomical Society, meeting at Northwestern University, there was a young graduate student by the name of Edwin Hubble sitting in the audience. So well received was the presentation that at its end, the 66 gathered astronomers leapt to their feet and gave VM a sustained standing ovation. It was the pinnacle of astronomical accomplishment to have gotten such difficult to obtain results and to have analyzed them with such virtuosity. While Slipher himself would remain skeptical of the island universe idea as expressed by Hertzsprung for a time, by 1917 he had come around to the Dane's point of view and presented his expanded work in that context to a meeting of the American Philosophical Society in Philadelphia. In the conclusion of his paper, he put forward the speculation that perhaps nebulae were scattering away from the Milky Way, a tantalizing hint of the expanding universe idea put forward some 15 years later by that same graduate student who had been sitting in the audience of his talk. By 1925, he would find the velocities of some 45 total nebulae, setting the stage for that later discovery. So why didn't Slipher see the expanding universe? Which is, I think, a really interesting question. I think there are 2 reasons. The first was that he didn't know the distance to any of them in any sort of way. Without that, I think, it's hard to see that there's going to be some sort of a relationship. Usually you want to plot something on a graph against something else, and he had only one of the 2 things. Nevertheless, in 1922, the German astronomer Karl Wirtz used a combination of a nebula's size and brightness to make an estimate of the relative distance of the objects. Simply put, if a nebula was larger in the sky and it looked brighter, it was thought to be closer to the observer. While that's not completely exact, it does give one sort of a benchmark. When the velocities were organized with respect to this rough measure, a surprising relationship was seen. The further away the nebula was thought to be, the faster it was moving. While not definitive proof by any stretch, it was an absolutely fascinating finding. The second thing going on here, I think, was while there is a possibility that all of those island universes could be moving away at the same time, it was hard to explain why they would be doing it. While Einstein had published his general theory of relativity just a year earlier, the ongoing Great War would slow the dissemination of that idea to the United States, and then, when it finally did arrive, most astronomers were perplexed by the mathematics and the constructs used to explain the idea of space-time that could curve and warp, and importantly for our story, expand and contract. Slipher's data was a part of a puzzle waiting for other data to come together. But the emerging picture was of a very large cosmos filled with a huge number of spiral-shaped island universes, galaxies, each like our own Milky Way, that were rushing away from us. Now, the other major development during this time was the rise of the Mount Wilson Observatory. The person, of course, who spearheaded this whole project was the enigmatic George Ellery Hale, who will most certainly be the subject of a later biographical episode. So interesting is his life. Just as Europe spiraled into the Great War, Hale was able to convince the Carnegie Foundation to invest a truly astronomical sum of money to build a new facility for him on Mount Wilson in Southern California. In 1903, he moved to Pasadena, California, with his family and soon decided that Wilson's Peaks, one of the prominences that could be seen from his bedroom window looking out at the San Gabriel Mountains, would make a fine place for an observatory. Here, he built a first-rate facility with first a 60-inch telescope and then, with additional philanthropic support, a 100-inch instrument that dwarfed anything in use anywhere in the world. It would be at Mount Wilson, of course, that Harlow Shapley would take his data for his work on globular clusters that would make him both famous and infamous. Shapley, as we sort of mentioned, was a risk-taker and a bit of a gambler, and so he reached his conclusions quickly and sometimes on kind of flimsy evidence. While most were supportive of his globular cluster work, there were those, especially at Lick, who questioned his methods and his results. Now, to be fair, what's interesting is that I haven't found a similar sort of doubt when it comes to Hertzsprung's work in establishing the distances to the Magellanic Clouds, even though that work used almost exactly the same methods in some respects that Shapley did. While this may be due to a combination of Hertzsprung's reputation and Henry Norris Russell's confirmational work that came up with a similar number, it seems likely that for many of those other researchers, it was the brashness and rough-hewn nature of Shapley's Missouri upbringing that may have put some of them off. It was during this time that Shapley made a number of close friends among the staff at Mount Wilson, including the Dutch astronomer Adrian van Manen. Now, during this time, as Shapley was working on his globular cluster studies, van Manen was making observations of spirals in order to see if he could detect rotation with that bigger 60-inch telescope. In other words, he's trying to do the same thing that Curtis had done some years earlier up at the Lick Observatory. Now, Shapley had come up with figures for some of the globular clusters that showed that they were at least 50,000 light-years away, which was a figure far in excess of Curtis's assumed 30,000 light-years for the entire size of the galaxy. As data kept coming in, that number kept increasing, thus expanding the size of the Milky Way until it was bigger by a factor of 10 from what Curtis had assumed. It was at this time that van Manen announced a bombshell observation. He claimed to have detected rotation in spirals, a result that almost certainly meant the death of the island universes hypothesis, as it would be impossible to have found motion if they were as far away as Curtis and Slipher were suggesting. For that to have been the case, van Manen argued, the spirals would have to be rotating so fast that the mutual gravitational influence of the stars would not be strong enough to hold these galaxies together. In fact, for the furthest ones, the stars at the edge of the galaxy would have to be moving faster than the speed of light, something that was known to be impossible due to Einstein's special theory of relativity, which had been published back in 1905. With these two converging results, Shapley, who had at one time been leaning in the direction of the island universes idea, now began to doubt those conclusions on the matter. He wrote to Henry Norris Russell, his old advisor, who, in a piece of advice eerily similar to what he would later give Cecilia Payne, told Shapley that he doubted Curtis's and Slipher's results in light of van Manen's announcements. As a result of this, Shapley did sort of a complete 180 and became a vocal advocate of spirals being nebula within a large Milky Way galaxy. Though he seems to have not been completely committed to them being places where stars were forming, he did have this sense that the galaxy and the universe were actually the same thing, and that everything lived within the Milky Way. With the notoriety stemming from his announcement of the Sun not being at the center of the Milky Way galaxy to propel his other views forward, Shapley soon became the most vocal advocate of this new position. He was now on a collision course with Curtis that would result in one of the most hyped scientific debates of the 20th century. "1920, in retrospect, was a tremendously watershed sort of year in so many ways. I think in many respects, it inaugurated what is often called the American century with the roar of jazz and motion pictures. It was the year women in the United States received the right to vote, prohibition was instituted instituted, giving rise to the speakeasy and juke joint, and, Johnson & Johnson introduced the Band-Aid adhesive strip. In astronomy, it is also known as the year in which the Great Debate happened. And yet, even with that grand title and all that it just sort of portends, the truth is really much less glamorous than the legend that has grown up around it. So this is how this went down. In 1919, George Ellery Hale had suggested to the National Academy of Sciences that the 1920 Hale Lecture, which, by the way, was named for his father, not for him, which, by the way, that lecture is always on a topic of interest to scientists, be given at the April meeting of the organization. He himself had thought that a discussion of Einstein's theory of relativity would be a good choice given its recent popularity, but the Academy's secretary, Charles Greeley Abbott, felt like the topic was already being a little bit overhyped, especially given what was going on in England with the eclipse date at the time, and maybe it was just a little too difficult to comprehend in such a setting, or, even more frightening, maybe, as some were suggesting, it was wrong, even in light of that most recent evidence to support its accuracy. His reticence and waffling on other ideas led Hale to suggest a discussion of the unresolved island universe hypothesis. Quickly, then, it was decided that Curtis and Shapley would be asked to present their positions in some sort of a discussion. Soon it was being billed as Shapley, the daring innovator, versus Curtis, the all-too-conservative observer. The truth, however, was nearly the opposite. Moreover, Curtis, the older and more experienced man, was significantly more comfortable presenting his ideas to a large group of his peers, whereas Shapley, at least at this time in his life, was, to put it mildly, ill at ease in such situations. However, in April of 1920, as the two men came together to have a discussion or a debate or a dueling presentation, there arose other agendas for both of them. Now, as we've mentioned several times, the death of Edward Pickering in 1919 had left open the position of the director of the Harvard College Observatory. Additionally, the Allegheny Observatory was also looking for a new director. Given this, both participants were working to establish their reputations, and so Curtis was kind of eager to, quote-unquote, go at each other with hammer and tongs, as he wrote in a letter to Shapley. He wanted to get all the issues out in the open and really air it out, or at least that's what he wrote Shapley. Shapley, on the other hand, wanted something a lot more formal and a lot more restrained for those reasons that we just mentioned. Moreover, what both men told correspondents was that neither of them felt like they really had good enough evidence to really make their positions on Spiral Nebula stick, and so they both were trying to get a little bit of wiggle room to go places in their research where they were on more solid ground, So, after a little bit of haggling about the format, the discussion was settled, and what was decided is that the two guys would give papers back to back, and they would not rebut each other, though they might take questions from the audience. They boarded the same train from San Jose to Washington, D.C., and on the trip they agreed they were not going to talk about the subjects of the talk so that their arguments would remain fresh. On April 26th, after earlier talks by Franz Boas and Robert Goddard, 200 to 300 people gathered at 8:15 p.m. to hear the two present their ideas. Unfortunately, and this kind of gives you a sense of just how low-key this actually really was, it was not well covered by the scientific press, and so we're sort of left to piece together what happened from notes and a few scattered and often unreliable recollections of the people who were there. We do know that Shapley went first, and we do have his typewritten notes, and so what we know is he spent a good deal of time covering what might be thought of as sort of basic facts of astronomy kinds of things, much of it on things like the size and structure of the Milky Way. When he did venture into new territory, he mostly discussed his big galaxy idea with only a small amount of time spent on what was thought to be the actual topic, and that is discussing these spiral nebulae and whether they were island universes or not. He then emphasized his result that the sun was not the center of the galaxy. It was, to be honest, pretty much a non-technical talk, delivered to, people who weren't actually astronomers, but rather sort of astronomically interested but talented professional scientists. And that these scientists weren't really involved in the nitty-gritty of the subject, and so they wouldn't be able to follow the really technical details. Now, the reason for this is unknown, though it was widely speculated that Shapley knew that several members of the Harvard Search Committee would be in the audience, as was in fact the case, and most of them wouldn't be professional astrophysicists working in the fields. In other words, what he tried to do was tailor his talk to make it more understandable for the men that he hoped would hire him. Now, Curtis, therefore, had to be really pretty dismayed by Shapley's approach, as he came prepared with all manner of evidence and data and thought they were really going to get down into the weeds of all of this. Unfortunately, we don't really have Curtis's notes. We can't find them. And so all we've got are a few slides with a little more than just bullet points. It'd be like having, half of the guy's PowerPoint presentation. And so it's hard to reconstruct what he might have actually said. The impression that we have from various accounts is that his talk was more technical, but it was also a good bit more spontaneous. He had to rework on the fly the tenor and possibly the content of his talk so he would not bring up responses to points that Shapley never made. At first, he focused on the issue of the size of the galaxy and the sun's position in it, disputing Shapley's methods for establishing the distances to Cepheid variables. He then went on to focus on the spirals, laying out his evidence in some detail, as we've already discussed. In hindsight, the discussion, I guess we'll call it, or the presentations, have really two salient features. First, the two presenters were really talking about different things. If you had come to hear a debate, that's not what you got. Shapley mostly talked about the size of the Milky Way, and Curtis mostly talked about whether the spirals were inside of it or not. They didn't really address the same kind of thing. The second is that what we know nowadays, again in hindsight, is that they were both right and they were both wrong. The Milky Way is big, though it's not as big as Shapley thought, and the sun is way off the center. So in those cases, Shapley was right. But the spirals are not inside of it. They're even further away. In fact, many of them are even further away than guys like Curtis thought. So, Curtis was right in that, and Shapley was wrong. The thing was, though, Shapley probably had the better evidence, or at least more direct evidence for his argument than Curtis did. On the other hand, in terms of the impressions from the night, Curtis came out to be the clear winner. As expected, Shapley was nervous, he was tentative, he was unimpressive in his presentation. Curtis seemed to be more in command of the stage and of the information. He came across as more forceful and more mature, something not lost on the Harvard committee members who, upon their return, would advocate for the hiring of somebody else, specifically Henry Norris Russell. What's interesting, however, was that this wasn't really the end of the debate. Both men were asked to provide papers representing their positions to the Bulletin of the National Research Council, wherein they could respond to and rebut the other authors' arguments. In other words, what's really true in this is that the real debate took place within the pages of a scientific journal rather than on a stage. Over the course of the next several months after the initial presentations, the two men exchanged drafts of their what were supposed to be 10-page submissions, thus honing each other's contributions significantly. As a result, each paper expanded to 24 pages, but they were significantly better for it. In the end, of course, it all came down to Van Maenen's observations. If they were true, Curtis had to concede Shapley's position. But science doesn't stand still, and in the period afterwards, additional evidence, some gathered by Slipher, and other evidence gathered by the Swedish astronomer Knut Lundmark, seemed to support the island universes model even more strongly. There began again this back and forth that sharpened the debate. Curtis, however, wasn't a part of it. Instead, he left Lick to take a position of being the director at the Allegheny Observatory. It was a great opportunity to be an administrator, but not a great one to be a researcher. The facility was too outdated, and the city was making it too hard to observe to keep up with the cutting edge of what was being done at high altitudes out in clearer skies. Curtis would later admit that he regretted making the decision to move to Pittsburgh. For his part, Shapley did, of course, in fact, damage his chances on the Harvard position, and it was offered to Russell. The Princeton astronomer considered the offer with the understanding that Shapley would be brought in as sort of an assistant director in order to give him more time to mature and grow into the sort of scientist who could take the reins when Russell retired. Princeton, though, hearing of the offer and not wanting to lose such an esteemed member of the faculty, made a counteroffer, and Russell eventually decided to stay where he was. Harvard then offered Shapley kind of a position that wasn't really a directorship, and so he declined as well. In a bit of a bind, Harvard then came back, and apparently they did this on the recommendation of Hale, with a sort of chief of staff kind of thing, where Shapley would be given a trial run to see if it would work out with him being sort of in charge of things, where he would have sort of all of the authority and none of the permanence of actually being the director. As we know, though, that was soon amended, and he was given the permanent position after coming in and breathing new life into the institution of the Harvard College Observatory. The two men, now ensconced in the higher echelons of the scientific establishment, remained cordial over the years, exchanging letters and occasionally reminiscing. However, with Curtis's departure from Lick, the program of using the Crossley to photograph spirals came to an end. At Mount Wilson, on the other hand, a new and more powerful instrument came online, and a new man had come to put it through its paces. As I bring this episode to a close, please allow me to apologize for the delay in its release. I know that I said I might have to take a week off, but I'd really hoped to have, this thing done. However, the best laid plans, as they say. It's been a super busy last 2 weeks with visits to neurosurgeons to get checked out. By the way, the news is all pretty good for the most part there. Visits to in-laws that involved escaping, believe it or not, from 1977, and a 111-mile bicycle ride through rural Alabama on what ended up being 107-degree Fahrenheit roads. Add to that the start of school, lots of meetings, and a birthday celebration, and you have a recipe for not a whole lot of stuff getting written. I also need to apologize probably for the sound quality of this. As I record this, I'm presently sitting in a hotel room, specifically the Hampton Inn at Gaffney, South Carolina, where tomorrow I'll head a few miles south to get in position to see if I can observe the total solar eclipse. Hopefully the clouds will stay away, and I'll be able to do some cool observing. If I can, I'll try to post something to the website, thescientificodyssey.typepad.com, and to the Facebook page. If you're in a place where you can make a few observations, take a few pictures, etc., please consider sharing those with the rest of the crew. Of course, as always, be safe and don't do anything to damage your eyes or your camera equipment. Finally, as the world starts to move towards the rhythms of fall, here in the northern hemisphere anyway, or the renewal of spring for those of you in the southern hemisphere, I hope you'll consider doing the podcast a favor. As many of you know, the best way to promote something is by word of mouth. While I know that some of you have done this already, if you happen to know, or think you know, somebody who you kind of think would get something out of the show, maybe it's a college or high school student, maybe it's a coworker, perhaps it's someone at the gym who needs something to listen to while working out, won't you tell them about the show? Here in the United States anyway, with all of the tough news that's been coming out lately, I think it would be great to offer people something a bit uplifting that talks about the power of the human intellect and the process of discovery to make for a better and more understandable world. Anyway, I hope you have a great week, and in their next episode, we'll take a look at the work of the perfect man. Or at least, that's the picture he wanted to present of himself to the outside world. Until then, full sails on your journey.